I will be presenting in this video the Darmok system and an analysis of the online case-based planning methodology presented in the paper similarly named by Santi Ontanon, Kinshuk Mishra, Neha, Sugandh, and Ashwin Rarn. It is well known that game AI is unable to compete with more experienced human players in RTS games. This paper presents a novel architecture for online case-based planning in order to address online planning given a time-constrained system. This architecture presented herein is named Darmok and is tested against the built-in AI of the game Wargus, a game similar to Warcraft. Case-based reasoning is a solution to new problems based on the past solutions of old problems. Case-based planning is an extension of CBR that merges both planning and learning. Online CBR and CVP are online adaptations of CBR and CVP. This paper presents an OLCVP architecture. Traditional CBR is applied only to static domains due to time constraints, or in dynamic environments where there's no restriction on planning time. It's not well suited for real-world applications like robotics, self-evaluating cars, and game AI. Past CVP systems include Chef, Prodigy Analogy, Prior, Nonlin, Mayor, Sins, Nasal, and IPEM. OLCVP typically has a large decision space that must be explored. The state space also changes with every game state update, which means that there are a massive number of combinations that must be considered. The system is non-deterministic. Decisions must be made based on incomplete information sets, so you have to examine what is known to be known, what is known to be unknown, and what is completely unknown. You must execute in real time, or the system will be ineffective. Finally, you must select plans based off of goal similarity, current state similarity, and adaptation cost. This is an example of two OLCVP models. The model to the left is very similar to Darmok. The model to the right is not explored further in this paper, but is an example of another model. The Darmok system learns to play from the observation of human or AI play, but is currently unable to use this data until the trace generated by the play has been annotated by a human. The Darmok system will then generate snippets from the annotated play and will store those snippets for later retrieval. Snippets will be discussed in further detail later on. The Darmok system is composed of two states, learning and execution. In the learning state, the system observes play to generate a trace. The trace is then annotated, analyzed, and stored for retrieval. In the execution state, the Darmok system retrieves, adapts, expands, and executes plans based on the current game state and the current system's goals. The Darmok system requires the following information about its environment: goals, primitive actions, vocabulary for conditions, features to present the game state, annotated expert traces, and rules for pre to post condition matching. During the execution of the Darmok system, planning and execution must be interleaved in order to maintain real-time execution in the system. The Darmok system performs no searching of the game state in an attempt to find matching snippets. Pictured here is the flow diagram of the Darmok system. The Darmok system interfaces with Wargus and the given expert traces, but otherwise is mostly self-contained and needs few primitives in order to be able to interface with the game as an AI. The Darmok system could easily be adapted to another RTS game by exchanging the expert traces and the primitives provided to the game for another game. Plans in Darmok are composed of snippets and goals. Snippets contain preconditions, alive conditions, which are required to continue executing the current snippet, the actual plan, which contains sequences, parallel execution blocks, actions, and sub-goals, and then the goals of the plan. In order to represent these plans, the Darmok system requires that it is provided with basic actions, sensors in order to obtain information about the current world state, and a set of goals in order to understand how the world works. The learning state begins by generating traces. These traces are generated through observation of play. The play may occur between AI players or human players. The traces then generated need to be annotated. This annotation is what allows Darmok to break the trace into snippets. The Darmok system does not currently implement plan recognition techniques, but it may do so in the future. Traces contain an action, the player that called the action, the cycle in which the action was called, and an annotation. These snippets are then stored in the case base for future retrieval. After the learning stage completes, each snippet is then associated with exactly one episode. Pictured above is an annotated expert trace. The annotated trace may then be passed to Darmok for analysis and future use. In this slide, we see a representation of extracted cases from an annotated trace. These cases are then stored, as previously discussed, for future analysis and retrieval. The plan retrieval module functions by contacting the case database and analyzing which episodes will have the highest predicted performance in the current situation. The case base contains snippets and episodes. Episodes are constructed from a snippet, goal, situation, and outcome success degree, forming a four-tuple. Following the learning process, each snippet is then associated with exactly one episode, but during play this will change as new episodes are created. This is how the system learns over time and is able to gain experience. In order to retrieve the best snippet, the case base will be assessed to find an episode with the highest performance, which is determined by examining episodes with the highest goal and state similarity, and then analyzing up to 5 of the best episodes to determine of those episodes which has the best performance. Plan adaptation is then delayed as long as possible in order to minimize error over time. Plan expansion and execution modules. Plan expansion, execution, and adaptation all occur in parallel. This creates a partial plan tree containing goals and snippets. Initially, this tree only contains the root, which is the win goal. Snippets and the goals are then added based upon plan retrieval, discussed in the previous slide. The state of snippets in the tree will either be pending, executing, succeeded, or fails. Goals become ready when all snippets that the goal depend on have succeeded. Pictured here is an interleaved expansion and execution flow state. Here we can see how the Wargus system interacts and how the plan tree is set up, with the win goal as the root, which links to a snippet, which then links to 3 other goals. Darmok's plan adaptation module aids in making retrieved snippets more relevant. This adaptation can be further broken into 2 segments, parameter adaptation and structural adaptation. Parameter adaptation will adjust certain parameters based upon the current state of the game. In this implementation of Darmok, this is seen as unit adaptation and coordinate adaptation. This means that the Darmok system will not try to select the same unit in a previous snippet, as the unit might not exist in this current state. This also means the Darmok system will try to change the coordinates if needed, as the coordinates given in the last snippet might not be valid. The coordinate adaptation is not easy, as it means that in certain cases the Darmok system will need to analyze why those coordinates were chosen, and then adapt the coordinate appropriately. The other adaptation that Darmok makes is structural adaptation. In this, the plan tree is dynamically modified based off of the condition of different nodes in the tree. The first thing that Darmok needs to do is create a dependency graph. This dependency graph is then analyzed to find what nodes might be able to be removed as they're redundant or unnecessary. Whenever Darmok notices an unsatisfied precondition, on the other hand, it will attempt to insert additional actions so that the unsatisfied precondition can then be satisfied before continuing the execution of the program. The Darmok system was tested in the game Wargus. The Darmok system was trained using an expert annotated trace, between 1 and 10 traces to be exact. The number of traces varied as to examine the effect that the number of traces had on the operation of Darmok. The system was also tested on 12 different maps and 10 demonstrations. To test Darmok, the system was evaluated by placing it against the built-in AI of Wargus. This built-in AI was a hard-coded AI. The Darmok system was tested in both a non-adaptive mode and an adaptive mode. Pictured here are 2 example maps that were used. The shown maps demonstrate the variety of operating conditions that the Darmok system needed to operate in when facing the enemy AI. When placed against the built-in AI, Darmok acquitted itself well and displayed its adaptation capabilities over a series of expert traces. As the number of traces grew, Darmok was able to obtain a steadily higher win rate, as opposed to the system without adaptation. The Darmok system managed to successfully run an OLCVP algorithm in real time in the game. The system was not only able to execute in real time, but was able to execute at 10 times the rate of the built-in AI, proving that the OLCVP architecture presented here is capable of executing in real time. Through expert traces generated in human demonstrations, the Darmok system was able to learn and plan so that it was able to play the game with a fairly admirable 41% win rate against the enemy AI. It must be noted that the Darmok system presented here has strong strategic capabilities, but displayed weak tactical control in smaller engagements. This could in turn be improved by granting the Darmok system an assistant, lower-level AI to control tactical engagements at a lower level, while retaining the high-level Darmok system for strategic engagements. Alternatively, the low-level tactical control could be scripted, as it is for the built-in AI in Wargus. Many of the games were lost due to this poor low-level control. The Darmok system gained a 2-fold gain in its win rate when it used adaptation as opposed to not using adaptation, which was not covered much in this paper but is instead a topic for future work. While the Darmok system in the state that it was presented was able to successfully attain its goals, it still needs to be further improved and examined, particularly the capability of Darmok to learn from experience. As part of the future work, the team plans to incorporate better recognition techniques. This could be particularly useful because the plan because of plan recognition. The Darmok system could observe human play, for example using Twitch TV, and then create expert traces from such play. By doing this, the Darmok system would need little to no human authoring and could continue to grow. Currently, the Darmok system cannot create conditional or looping plans. This is a system limitation that can be fixed so that the system is able to create richer behavior. Furthermore, the Darmok system needs to incorporate better scheduling techniques. When the team observed the performance of the current Darmok system, they recognized instances in which the system lost due to poor scheduling and coordination. This could be resolved by incorporating a scheduling system as a filter. Finally, the Darmok system can be improved to be more preemptive. This will allow the Darmok system to recognize that a plan may fail and correct or change the plan that is currently executing so that smaller losses occur. Thank you.